Welcome back, chemistry fans. Kicked out of my own bedroom. All right, let's start topic 4 for unit 2. Let's talk about percent composition. Let's share our screen here and get started with it. Okay, percent composition. It is just a simple analysis of what percentage does a specific element make up of an entire compound. You could talk about this in terms of things that you understand to make this a relative concept for you to understand, like the human body. We all know, they say that it is about 80% water. Reality is it's probably somewhere in the 75%, and it's probably even less than that. It's just that we are taking oxygen, all of its compounds, and the hydrogen amounts and combining them together. Well, that's rather naive because these two elements are actually bonded with other elements in our body. But if you just assume that those are the only two that combine together, then yeah, we're about 75% water. Earth's crust. Notice what majority of the Earth is made up of. It's mostly made up of oxygen. And you're like, well, what? We're not floating on air. It's combined with other elements. So one of the biggest chunks of material is silicon, sand. And then aluminum is the next big. And then we got a ton of iron and calcium out there. Okay, so how we come about those percentages is you have to understand percentages as a concept. It's individual amount divided by total amount. So if I had 100 pieces, 11 of them would be in this orange, 89 of them would be the green. The individual amount would be 11 divided by 100, and that would give us 11%. If we were talking about in this bracelet, what is the percentage of green? Well, there are 20 beads in this, so we would do the math. We would take 2 divided by 20, and that would give us 0.1. We multiply by 100, and that's where we get 10%. Same thing for any of the other pieces. We would do the exact same formula. For the pinks, it would be 9 divided by 20, and that's 0.45. You multiply it by 100, and you get 45%. In chemistry, what we're going to do is we're going to do it by mass. So we're going to take the individual weights of the elements divided by the total molar mass. The elements all may have added up together in the compound, multiply it by 100. So let's go ahead and do this. So what I'm going to do is I'm going to go and get the weights off the periodic table. Silver, if we go and look up the weight on the periodic table, it sits right here in the middle. It's 107.87. So we will write that one down. Click between these two screens. So 107.87. Plus, there's going to be 2 of the chlorines. Well, let's go find out what the weights are over here on the right side. Element number 17, 35.446. 35.446. Now, the great news is I did not bring a calculator. So hang tight. So here we go. 107.87 plus 35.446 times 2. And what you get is 178.76 sig figs there. The 2 that was the last digit got cut off. We don't use that one. So just be 0.76. Okay. Now, here's what we got. We have to now, that's the molar mass. What we're given the task is to find the percent composition. So let's go for silver. It's easier. It's got 1 digit already written down for it, or it's got 1 value already written down. So 107.87 divided by 178.76. 107.87 divided by 178.76. And we would get 0.6034. And it looks like we would actually use a 5th digit for 3. Multiply that times 100%, we would end up with 60.343% silver, meaning that the remaining balance would be 39.657% chlorine. How do we come up with that? We subtracted 100 from 60, and you get the other half of that. All right, let's do another one over here. Let's do the barium one. I'm going to change my pen color so you'll be able to see it. So barium off the periodic table weighs 137 point, I'm not sure, 137.33. So I got 137.33 plus 2 of the oxygens, which are 15.9994, plus 2 of the hydrogens, which 1.0079, I believe, 1.0078. What this one says. 0.78. All right. Add all that together to get our total molar mass. Plus 2 plus 137.33 and roughly we get 171.3455. This time I'm going to keep all my sig figs until the last step whenever we do the division, and that way we'll have a more accurate reflection of what the sig fig is. So that's my total amount. So again, what I'm going to do I'm going to start with the one that has only one value. So I'm going to take the 137.33. I'm going to divide it by 171.3455. 137.33 divided by 171.3455, and you get roughly 0.80. I got 5 sig figs, so 148. Sorry, 148. I'm not sure how I misread that. Okay, now multiply that by 100, ends up being 80.148% barium. Now I can't subtract from 100 to figure out what the percentage of oxygen is, because there's also a hydrogen out there. So what I'm going to have to do is I'm going to have to do my my percentage here for that one. So I'm going to take 31.9988. That's the weight of both of the oxygens together, divided by the total weight, 171.3455. 171.3455, and I would get 0.1867. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I gotta get 6 figures out of this. Oh my gosh. I'll multiply that by 100, and I would have 18.6750% oxygen. And now I can, in fact, do the last step, which is add those two values together to get my final percentage. 0.148. And I will get, for the hydrogen, I am oh my gosh, small, so small. 1.1, and I would have 1, 2, 3, 4, 5 sig figs. 5 sig figs. 1.1770% hydrogen. Okay. Hopefully, you're going to be okay with doing those 2 examples. If we need more, we can do those in the homework. You can ask for some extra practice problems, but I'm going to move on to percent error. Percent error is just like a percent composition. It has nothing to do with the atomic masses. It's just a very intimately related topic where we take individual amounts divided by total amounts. Well, in this case, the individual amount is the difference between the 2 values, the right value and the wrong value, the correct value and the wrong value. So if you want to substitute in here, we could say the approximate value, well, that's the wrong value, and the exact value, that is the correct value divided by the correct value, however you want to word it. Notice that it is absolute value on top. So it doesn't matter which one you subtract. If you do wrong minus correct or correct minus wrong, it's an absolute value. It always ends up being a positive value. But what must go on the bottom always is the correct value. So let's do a quick little, here's another version of it, experimental. What are the values from the experiment? What are the values from the actual truthful values that have been tested and true by someone else? Let's do some practice now. Supposed to be 50 grams, but you end up with only making 40 grams. Supposed to be, that means this is correct. This is my wrong. So I'm going to do correct minus wrong divided by correct. And if you want to do wrong minus correct, I'll show you it's the exact same value. So 50 minus 40, absolute value, divided by 50. That is 10 divided by 50. If I do wrong minus correct over correct, it's 40 minus 50, absolute value, divided by 50, which is also 10 over 50. It does not matter. What you end up in both cases is 0.2. You multiply it by 100% to turn that into 20% error. Let's do one more. A student. The student always makes the mistake. So the student is where the data came from the lab. So the wrong minus correct, 404 minus 390 divided by 390. So the difference there is 14 divided by 390. This error is going to be rather low. The other one was a 20% error. This one's going to be significantly lower. Times 3. And I get 3 with 3 significant figures, actually only 2 significant figures. So this would be 3.6%. There's only 2 significant figures. The last 0 does not count as significant. Okay. Last topic that is related to this. If you understand the percent error formula, it's how wrong you are. Well, what would be the formula for how correct you are? Well, you would hope that they would call that the percent correct. They don't. They call it the percent yield. So we must get used to that idea in chemistry. Percent yield is how correct you are. And all it is the wrong divided by correct. That's how you can reword this. Wrong divided by correct. If you get that down, you would then have your percent yield. Actual over theoretical, those are some of the values that, or those are some of the synonyms that you can utilize to solve this. Okay, so here we have similarly worded questions from before. The accepted value is 80, the experimental is 71, so I'm going to do 71 over 80. And I get 0.8875, round that to 1 significant figure, actually, because the 0 is not significant. And what we'd have is 90% yield. It would be a 90% correct. Let's do the same thing down below. A student has 404. It's supposed to be 390. So last time, remember, it was somewhere in the 80s was our percent that was correct. This one's actually going to have too much. So let's see what our yield is. It's going to be more than 100%. 404 divided by 390, and we get a 1.03, meaning this has got to round up times 100%. It ends up that we had 100% yield, which doesn't make sense. You can't have more than 100%. You probably could never have 100%. There's not an absolute perfect process for manufacturing. But that's not the point. All right, so thank you very much for your time. Hopefully you will have a little bit of practice with percent yield and percent error, remembering that the addition of the two of these will equal up to be 100%. If you add percent yield and percent error, it's going to be 100 always. So as long as you know one of the formulas, you actually kind of know both of the formulas. Okay, that's it for this topic. Thank you very kindly. I will talk with you again soon. See ya.